So constructing index is actually pretty straightforward. It's mainly a question of performance issues to get it built properly. And you just obviously assign little integers to every document and every term. These are the labels of the rows and columns of this matrix we discussed. And we just create a list of triplets, term ID, document ID, and term frequency with the attached location and other types of information we may want to keep. Then we have to sort this list initially on term ID. That will allow us to take all these doc ID, term frequency, location for a particular term ID and associate all the term ID triplets, all triplets for the same term ID together. And this is transposition because you start off with a document with something arranged by document, and you want something arranged by term, and that's yet another simple example here. We have six documents. We have 10 terms in those documents after we do all our reduction to normal forms of these 10. These are the 10 index terms. And then we form, these are the 6 documents. That's this matrix. Here's the 6 documents. Here's the 10 terms. You start off being arranged by document, so you have everything for document 1, then 2, 3, 4, 5, 6. But actually you want it arranged by words. You want all the stuff for word 1, then word 2, then word 3, and so on. And that's what that's sort of illustrated here. This is really quite straightforward. So as I already have mentioned, this is actually sort of trivial because sorting is incredibly well understood. And the only issue is scalability and size. And that's what you'd expect for big data. And so we have to essentially go back to the traditional computer science literature and find out how to do sorting. And there are various, there's lots of work in this area. And we have to do clever compression because it's important not to minimize disk access. And one possible approach, which is pretty natural, is to do merge-based sorts, which is that you take a part of the sample, you do its, you form the inverted index for that sample, then you do another sample, and then you have 2 completely sorted lists, which are now sorted by documents. And then you know that merging is actually more efficient than sorting, so you can merge those 2 documents into a single list. And that can all be done in some very fast, well understood fashion. So, and of course, again, it's all performance. So you need because of the size of the data and the number of users all demanding 1/10 of a second response, you have to use replication to get enough servers to be able to respond to all users. You have to distribute the data in an intelligent fashion, and there is no, I don't think there's much rocket science here. It all depends on the current size of your disk, the current size of your problem, and there are all sorts of obvious caching type methods. And you keep things stored. So in the memory, which are the responses to very common queries and things like that. And as we've noted already, data compression is very important. We want to get as much as possible into memory, so we compress the data to get it in memory. An important feature of this problem is the fact it's dynamic. The web is changing every day, and you need to be able to change the index to reflect that. And you do not remake the index for every time a website changes. You don't remake that index. Rather, that's just too inefficient. Rather, you You can do it in several ways. The most obvious is to have a basic index, and then you have a new index, a second index, which is all the new data, and you find things first in the new data. You invalidate things in the old data based on the new data, but then you add the non-invalidated, which is the dominant part of the information from the old data. Then when the auxiliary index, the index of new data, gets too big, you merge it with the main index.